So, I thought that I would share with all of you the inside story of black hole stability. So let me give you very quickly an outline of what I'm going to tell you. So I'm going to begin by telling you a little bit about the interior of black holes. This will be review for most of you, either because you're experts or because you've just been at this summer school. And in particular, this introduces naturally something known as the strong cosmic censorship conjecture in general relativity. And this conjecture is very much related to something called the Blueshift effect. So then I'll have a little diversion and talk a little bit about the Blueshift effect in linear theory. And then I'll actually be able to present what is a resolution of the general problem of the structure of generic black hole interiors. And finally, what is left to be done. So as you'll see, even though this is about the inside story, the outside story will also rear its head several times during the talk, and I'll say a few things about the outside story. Okay, so that's what I hope to do. So let's begin with sort of the interior of black holes that we know and love, and how that leads us to the strong cosmic censorship conjecture. So the whole discussion, if you want, begins with Schwarzschild spacetime, which I'll assume that by now you're all familiar with. So we all know that Schwarzschild spacetime is geodesically incomplete. And more specifically, all observers gamma, which enter the black hole region, so here's such an observer depicted, they live for only finite time. So proper length of these time-like geodesics is finite. But it turns out that it's not just that they live for finite time. There's a good reason why they only live for finite time. And the good reason is that they are torn apart by infinite tidal forces as they approach r equals 0. And a related statement is that this Lorentzian manifold M comma G is inextendable as a Lorentzian manifold with C0 metric. Okay, so in a very, very strong sense. Okay. So moreover, something else very familiar to everyone here, presumably, is that this singular boundary r equals 0, it can be represented naturally as a boundary space-like hypersurface of spacetime. Okay? So this is all depicted schematically in this Penrose diagram of Schwarzschild. So that's Schwarzschild, and we all know that. But we also know that things change completely when you look at Kerr. Right? So Kerr is still geodesically incomplete. But now the part of spacetime which is determined by initial data, so that's the darker shaded region which is depicted here, is in fact smoothly extendable beyond no boundary, known as the Cauchy horizon, to a larger spacetime, m tilde, comma g tilde. And in fact, all finitely living observers in the original spacetime, they can indeed pass into this new sort of extended spacetime to live another day. So that's great, except that these extensions are highly non-unique. That's the whole point. These extensions, by causality, let's see if you understand these depictions, they are not determined by Cauchy data. Okay? So we have no idea what happens to these observers. So, well, which of these two situations is preferable? Well, I guess if you're the observer gamma, you probably think that the second is preferable because, well, you get to live another day in this extension in the second case, whereas in the first case, you're torn apart by infinite tidal forces. That doesn't sound so pleasant. But actually, from the point of view of bureaucracy, it is the first case which is far more satisfying. Because in bureaucracy, we very much want everyone to be accounted for. And in the Schwarzschild spacetime, all observers, they either live forever, and that's great, and we know what happens to them, or they don't, in which case they are torn apart by infinite tidal forces, and we also know what happens to them. But in the Kerr case, we have these observers who go AWOL and are unaccounted for. And so the bureaucracy doesn't like that type of thing. And neither does physical theory, because we want our physical theory, like bureaucracy, to account for everybody. And in fact, this is extremely, extremely problematic from the point of view of the sort of physical admissibility of general relativity. And it was first Penrose who suggested a way out of this, what seems to be a very funny physical situation, which is given already by the Kerr solution, which is one of the most basic solutions of the theory. And the way out is essentially the statement that Kerr is a fluke. Okay? That, okay, Kerr happens to be like that, but generically, the situation is more like Schwarzschild. Okay? And this conjecture, which goes by the name of strong cosmic censorship, so formulation of this conjecture is that for generic initial data, for the Einstein vacuum equations, then the maximal Cauchy development should be future inextendable as a suitably regular Lorentzian manifold. Okay? So this is a true statement about Schwarzschild. Okay? It is a false statement about Kerr, even sort of no matter how, what regularity you put, Kerr is smoothly extendable. Okay? So it's certainly a false statement about Kerr, but the conjecture says that generically, you should have an extendable. So more colloquially, if you want, you can think that this conjecture says that generically, the future is uniquely determined by the present. Okay? But it's very important that already the existence of the Kerr solution tells you that the best that can possibly be true is that this statement holds generically, okay? Not for all initial time. So I've on purpose been coy on what is the right formulation of suitably regular, and we will return to this in the talk. All right. So well, we've all read our Marx, so we know the poverty of philosophy. So fortunately, Penrose was not guided by philosophy or wishful thinking alone in making this conjecture. It was not just because he wanted it to be true to sort of save the respectability of general relativity as a deterministic theory. But there is a sort of possible mechanism that he first identified that suggests that this could be true, and this is the celebrated Blueshift instability. So this is in fact dual to the Redshift stability mechanism that Maciek discussed already in his talk. And essentially, we can understand this as follows. So this is really an effect of geometric optics. So if you have two observers, A and B, so A is the more conservative one and sort of stays outside of the black hole, lives forever, happily. Observer B is the more revolutionary one. So observer B in finite time enters the black hole region, and then sort of in finite time will exit the Kerr spacetime, crossing this Cauchy horizon. And if you imagine that observer A sends a signal at a sort of constant frequency as observer A measures that signal, and you look at the frequency of the signal as it's measured by observer B, then just because sort of the time lengths between the crests, if you want to think about it like that, goes to 0 in B's time, just in view of the fact that B in finite time crosses that boundary CH+, this tells you that this signal is infinitely blue-shifted as sort of, B approaches his or her Cauchy horizon crossing time. Okay? So this is just, if you want, geometric optics. And, well, Penrose argued that this Blueshift would cause linear perturbations to blow up along this Cauchy horizon CH+. And if you want, this then suggests that once you have a wave-like dynamic degree of freedom, like you do for the Einstein vacuum equations, then this should be an instability, and thus the formation of such Cauchy horizons should be unstable. So this is what he said, and this is precisely the history of the formulation of strong cosmic censorship. It's precisely this argument. Okay. So let me make an additional comment, which is the following. Of course, linear equations on a globally hyperbolic background, they can only blow up asymptotically. Okay, so in linear theory, you know a priori that the worst that can happen is somehow linear perturbations blow up in some sense asymptotically at the Cauchy horizon. But of course, the Einstein vacuum equations are nonlinear, and it's reasonable to suppose that, well, once sort of linear perturbations get very big, then you become inside of some nonlinear regime, nonlinearities kick in, and this would cause sort of blow up to occur before the Cauchy horizon, making the singular boundary space-like, as in Schwarzschild. So if you want an actual working hypothesis, in view of the fact that Schwarzschild was really the only other example, was that generic dynamic solutions of the Einstein equations, at least in a neighborhood, let's say, of the curve family, would look like this. Okay? So the generic picture would revert back to Schwarzschild. Right? So it's sort of funny, because if you look at Schwarzschild itself, it is a non-generic member of the sort of curve family. All right? But if you look more generally in the class of sort of dynamic solutions of the Einstein equations, the generic picture, according to this, should be like it. So let's even formalize this, because in fact this is the colloquial version of strong cosmic censorship that one often sees. So I will call very strong cosmic censorship the statement that for generic vacuum asymptotically flat initial data, then the maximal Cauchy development is future and extendable just like Schwarzschild was. That's to say, as a Lorentzian manifold with continuous metric. Okay, so in this very, very strong sense. And moreover, that the singularity can be naturally thought of as space-like, whatever that means. Okay? So the Penrose diagram looks like this. So I'll call this very strong cosmic censorship. So there's actually a reason why this is really the form of the conjecture that is often thought to be true. So in physics, one is never shy of making very ambitious conjectures. So there is an even more ambitious conjecture than very strong cosmic censorship, which is known as the BKL conjecture. So this conjecture has been very influential in sort of setting the agenda for all discussion of singularities in general relativity. So if you ever see the discussions of generic singularities in general relativity, sort of even the language in which you talk about it has been conditioned by this conjecture. And this conjecture gives a very precise description of the asymptotic profile of generic vacuum singularities. And part 0 of this very precise description is that they are space-like and that you have inextendability in the sense that I said. Okay? So in some sense, very strong cosmic censorship is just part 0 of a much more ambitious conjecture known as BKL. And so in particular, I'll just distill this statement. Okay. So so that's the, if you want, introduction to the problem. So let's talk a little bit more about this Blueshift effect in the context of linear theory. In fact, it's rather interesting that even though sort of this effect had been discussed already, so this sort of these considerations of Penrose date back to the late 60s, early 70s, there really wasn't any sort of mathematical work on really quantifying this Blueshift effect in even just in the context of linear theory. And this is, in fact, even this is very recent. So first of all, there is a sort of a very general statement that you can get. In some sense, this you can think of as the simplest mathematical realization of this heuristic account of Penrose of the Blueshift instability. And this, you get it as what one can think of as a corollary of a general, recent theory of the Gaussian beam approximation tailored to general Lorentzian manifolds, particular manifolds that don't have time-like killing fields for which there's a natural notion of energy that you can talk about. And so this is a theory, if you want, in the spirit of ideas of Ralston, which is due to Jan Zbierski. And the sort of corollary of this theory in this context is the following statement. I might as well draw it. It's sort of easier. So let this be Kerr, and in some sense, I'm only going to talk about solutions of the wave equation in the domain of dependence of some. Well, I mean, if you want, I can do the two-ended. It's okay. It's not a problem. So this is Kerr. So this is a Cauchy hypersurface. Let me give it the same notation that I called it here, sigma. And this is some space-like hypersurface, which I'll call sigma tilde, okay, which is inside the black hole, okay, and meets the Cauchy horizon, okay. So the sort of statement that you can get for free is the statement that there can be no uniform energy bound of energy of solution through this hypersurface in terms of energy here, okay. As opposed to actually, if you look at the foliation of this region by suitable hypersurfaces, then there is such a uniform energy bound. We'll discuss that later, in fact. But you can show that just on the basis of Gaussian beam approximation and this geometric optics effect, that there can be no such sort of bound here. Okay? So this is sort of a result that you get for free, and it's a nice general statement that you can make. On the other hand, you shouldn't think that this is really capturing the story of what's going on. And the reason is that, you see, the perturbations that we actually consider in general relativity are not finite energy perturbations, but they are localized perturbations. So localized perturbations will actually sort of, this is the graph of the perturbation. In some sense, they will decay. Okay? And you might think that there is some competition between sort of how these decay and the strength of this blue shift. And in fact, there is such a competition in principle. So, so a theorem that you can actually state in the simpler sub-extremal Reisner-Nordstrom case. So you know Reisner-Nordstrom is often used as a toy model for Kerr. It's a spherically symmetric solution of the Einstein-Maxwell equations, which has the same causal structure, let's say, as Kerr. What you can say is the following, that if you know that there is a lower bound on the decay of the spherical mean of a solution of the wave equation on the event horizon, a lower bound of this form, then the energy corresponding to this solution of the wave equation will indeed be infinite here. Okay. So this lower bound is conjectured to be true, but there isn't actually a proof that this is true for generic solutions of the wave equation, let's say, arising from compactly supported. Okay. So, but at least if you believe that lower bound, then you make a mistake. Okay. So there is some blow up, but it turns out that this blow up that occurs, the energy indeed becomes infinite, is actually weak in the sense that even though the energy becomes infinite, phi itself, that's to say the solution in L infinity of the wave equation, remains uniformly bounded in the whole interior region. And this is a recent result of a student of mine, Anne France. So the statement is that if you have a solution of the wave equation on sub-extremal Kerr or Reisner-Nordstrom, such that the initial data is sufficiently regular and sufficiently localized, okay, then phi, or C, I guess I'm calling it, will be uniformly bounded in L infinity everywhere. Okay. So it's actually interesting, so this result holds in the full sub-extremal range. It's actually interesting to look at the extremal case. There are some upcoming results of Gajic. The extremal case actually in the black hole interior is more stable than the sub-extremal case, which is slightly paradoxical because in the exterior we all know about the so-called Aretaichi's instability. So the solutions of the wave equation are more unstable in the exterior. So there's something funny. Sorry? By duality. So let me just say a few words about this proof of this theorem, which will appear soon, and it's actually I think a very nice place to start to learn about the wave equation on Lorentzian manifolds, which are less familiar. So the first element of the proof is actually the fact that we completely understand the exterior region, so in particular up to and including the event horizon. So this is, well, for the general sub-extremal range, a recent result of mine, Rodniansky and Schlapp and Rothman. And well, I'll sort of talk a bit later about the prehistory of this later in the talk. But in any case, the only thing that you really need to distill from that is that along the event horizon, you have polynomial decay in terms of a sort of suitable coordinate, which I'll call V. It's an Eddington-Finkelstein type coordinate, for those of you know, of this form. Okay, and you need sort of this flux. You can think of this as a flux to decay at this rate, and delta is anything greater than 0. So you need just a little more than 1. Okay. So actually, in the Reisner-Nordstrom case, this result is also known in the full sub-extremal range. You can obtain it from things in the literature by putting together some old work of Blue Sulfur and the other things which are written here. So once you have this, then you want to propagate sort of estimates into the black hole interior, and it turns out that there's a sequence of 3 regions that it makes sense to talk about. What I'll call a redshift region, which is the region near the event horizon. This is the same redshift that figured in Maciek's talk. Sort of a no-shift region when nothing much is going on. And then what I'll call a blueshift region. So this is really where the blueshift effect takes place, near the Cauchy horizon. In any case, going from sort of the event horizon to the sort of beginning of the blueshift region is not so difficult on the basis of sort of techniques that have already been developed in the context of the exterior problem, in particular sort of multipliers which capture the redshift effect. So the interest is really in understanding the blueshift region, and I'll sort of simplify the story quite a bit, but essentially it turns out that you can construct a vector field with sort of funny weights in Eddington-Finkelstein coordinates. So I say funny because these coordinates themselves are very funny if you think about them, what they mean locally. So this vector field of this form in the Eddington-Finkelstein coordinates looks like this in local coordinates. It's actually quite funny. And if you pick a p which is bigger than 1 but less than this 1 plus delta, this room that you have from the flux, then you can derive weighted energy estimates in the blueshift region corresponding to this vector field. And you finally control a weighted flux of this form. And then, well, you can think that uniform boundedness of phi follows from the boundedness of this weighted flux. So this is really sort of a cartoon of the proof. So let me just, before leaving the context of the blueshift effect, mention just as an aside another setting where the blueshift effect rears its ugly head. So, and this setting is scattering theory. So let me first remind you of a classical result in sort of scattering theory for the wave equation on Schwarzschild exterior. So, so it's a classical theorem of Dimmock and K that you can parameterize finite T energy solutions. So that's to say, you can look at the vector field d by, sometimes I'll refer to this vector field as capital T. D by dt, this is the killing vector field in the exterior. So we all know that the sort of vector fields define an energy space. Okay, so you can look at sort of this, the energy space along a hypersurface sigma naught defined by this vector field. I can denote that space by script E sub sigma naught. And so the sort of map that takes initial data in that energy space solves the wave equation and returns its sort of trace in that energy space in H naught plus and I plus. That's sort of a map which is trivial to define, this map, if you want, in view of just the conserved energy estimate. And the theorem of Dimock and Kay is that this is an isometric isomorphism, which means that you can parameterize all solutions of the wave equation in this sort of, which come from E sigma naught by scattering data. Okay, you give me scattering data in these flux spaces, okay, then there is a unique sort of initial data that gives rise to that. Okay, so there's sort of a reformulation of this in this conformal picture, which sort of is very attractive from the point of view of relativity. Nicolas has recently been in. Okay. So that's the classical scattering theory. But why does the Blueshift effect secretly rear its ugly head in the context of scattering theory? Well, turns out that, you see, you don't see this when you look at this funny conserved energy, exactly because the conserved energy is conserved, and the sort of vector field d by dt becomes null and tangential to the horizon. But if you look at sort of solving the wave equation backwards and look at energies which are sort of corresponding to local observers, that's to say, which are actually time-like on the event horizon, then when you solve backwards, you should see the dual of the redshift effect. You should see the Blueshift effect, because, again, if you imagine here two observers, A and B, okay, where B sends backwards a signal to A, okay, then again, if you know your Schwarzschild geometry, this length is much, much less than this length. Okay, so this signal is Blueshifted, and the Blueshift becomes infinite as you send B further and further ahead. So, this Blueshift already suggests that you should not sort of have a scattering theory in the norms corresponding to sort of local energy, okay, as opposed to the conserved energy. So it suggests that, but it's actually hard to show in general. But it turns out that in Schwarzschild there's some nice monotonicity, so you can in fact use that to make the following statement: that if I happen to know that the radiation field here is, let's say, exactly v to the minus p, okay, for p greater than 1, let's say, and if I happen to choose trivial scattering data on null infinity, okay, then using some monotonicity, you can actually show that the non-degenerate energy of this solution on the hypersurface sigma naught is infinite. Right. So a corollary of this is that if you look at the bounded map that takes a sort of finite local observers vector field energy solution to its trace here and its trace here, so this map has been proven to be bounded, this map is not invertible. Map is not invertible. So there is no sort of scattering theory in the local observer space in the sense that, okay. So, and you should always remember this is really, again, the Blueshift instability. Okay. So we'll say maybe later a few other comments about scattering theory. All right, so on to the sort of next topic, which is the resolution of this question of what is the structure of generic black hole interiors. So let's review where we are. So So what did we show about linear theory? And by linear theory now I really mean poor man's linear theory, just the sort of linear scalar wave equation on the Kerr background. What has been shown is that if we look at sort of solutions that arise from localized data here, then C itself is uniformly bounded in L infinity all the way up to the Cauchy horizon, but presumably its energy is infinite. Okay, that's to say, if you believe certain conjectures, then its energy is infinite. Okay? So let's naively extrapolate this to the Einstein vacuum equations, where we think about C as being the metric G, okay, and derivatives of C being Christoffel symbols. Okay. So if we just extrapolate linear theory and think that, well, the nonlinear Einstein equations will behave just like sort of the linear theory, then that would mean that we should expect that the metric, okay, remains bounded all the way up to this boundary. Okay? So in particular, that there is a sort of null boundary of spacetime to which the metric extends, maybe continuously. But the Christoffel symbols will not be locally square integrable here. So if you just naively extrapolate linear theory, this suggests that maybe generically you have sort of a boundary of spacetime, which is again exactly where it was in Kerr, in the sense of the conformal picture. The metric in L infinity close to the Kerr metric, so continuously extending to this boundary. But the Christoffel symbols not square integrable. Okay, so such a null sort of boundary of spacetime with this property, I'll call a weak null singularity. Okay? So, so this is what you would get if you naively extrapolate sort of linear behavior. And there is also some evidence for this for some very sort of rough, spherically symmetric toy models, which were fully nonlinear. Okay? So that's sort of what you get by extrapolating that. But on the other hand, of course, if you believe this original intuition and these very general considerations motivated by this conjecture BKL, then sort of singularities should be space-like, generically. It's just the way life is. And so whatever happens, the Einstein equations should actually, the nonlinearity should kick in. We should not extrapolate linear theory, and there should be a space-like singularity before, through which the metric is inextendibly continuous. Okay? So this whole talk is about the question of which of these two scenarios is correct. Okay. So first of all, if you see, one of the problems of believing that you can extrapolate linear theory in this way is that there are no examples known of vacuum spacetimes, sort of just a little patch of vacuum spacetime like this here, okay, which has as a boundary such a weak null singularity. Okay? There are no known examples previously in the literature. Okay? We all know examples of this. We have Schwarzschild. We have no examples of this. So if you believe that there's any hope of the first scenario holding, then you first have to tell me that indeed there produced at least one example of such a vacuum spacetime. So this was actually proven very, very recently in a breakthrough result of Jonathan Luke. And he showed that, yes, such weak null singularities locally exist. You can construct vacuum spacetimes in a little patch, which are bounded by sort of a null singularity of this type. And in fact, you can do this by solving an initial value problem, a characteristic initial value problem. So, no, I can't. I'll go there. Oh, I can erase this though. Jacques, there are buttons. Oh, descent. So the way you construct this is you prove a local existence theorem for characteristic initial data for the Einstein vacuum equations. So you set up characteristic initial data on, let's just call this an outgoing null cone. The word outgoing doesn't really mean anything in this context. So you'll have initial data here and initial data on a sort of conjugate ingoing cone. So this is a characteristic initial value problem for the vacuum equations, Goursat problem. And actually, the free data for the Einstein vacuum equations are parameterized by the so-called shear. So here on this outgoing, so the shear I'm going to notate by he hat. Okay, so this is the shear of this cone. It's a differential geometric concept. And if I call u bar a coordinate here, which is affine, all right, such that u bar is equal to u bar star here, I'm going to initially prescribe this, okay, such that it has this funny form. Okay, so that looks sort of funny. So don't ask me why. Okay. But you'll note that for p is greater than 1, this is integrable. So it is in L1. So that's consistent with the fact that the metric itself, this is a Christoffel symbol. So you integrate it, you get the metric. So the metric itself is continuous here. In fact, continuously extends. Just initial data. All right. But this is not in any LP for p bigger than, I shouldn't use the word p, LQ for q bigger than 1. Okay. So if you plug in sort of this type of initial data, then you see that this type of initial data is very singular. So in particular, already the level of initial data, you cannot extend this so that the Christoffel symbols are square integral. So, and here you put anything. It doesn't really matter. So his theorem is that you can solve the Einstein vacuum equations in a region like this. Okay? So that's part 1 of his theorem. And part 2 of his theorem is that, well, this behavior for the shear propagates. Okay? So in particular, this is indeed a weak null singular boundary of spacetime. Okay? Let's say it's a boundary across which you can still continue the metric continuously beyond, but the Christoffel symbols in such an extension will fail to be squared. Okay. So this is his theorem. And actually, you can think of this theorem as an extension of a sort of also recent, the previous result of Luke Rodnyansky on the propagation of so-called impulsive gravitational waves. So impulsive gravitational waves, actually, you create them with a similar setup. That's to say, you again prescribe a singular he hat. But he hat is actually much less singular than in the case of weak null singularities. He hat has a jump across a null hypersurface here. And in fact, you can continue this beyond, and it still makes sense to think of this as data. And what Luke and Rodnyansky showed is that you can sort of solve the Einstein vacuum equations in a region like this. So a region sort of including this singular front, and this singular front indeed propagates precisely on this null cone. So you can think of Luke's result as an extension of this, but in Luke's case, it's much more singular. So in particular, it is so singular that it does not make sense to talk about extensions as solutions of the Einstein vacuum equation. Okay. So that's Luke's breakthrough. And actually, maybe I should say that if you followed this Luke Rodnyansky theory, actually they not only considered the case where you have one singular front, but they also considered the case that you have sort of two singular fronts. So here, that's to say, you also have a singular front in this conjugate null cone initially. And they proved that, well, if you sort of set up the data to be small in a suitable sense, of course, you have these singular fronts. So it's not the small data problem, but sort of small in some other sense. Then you can control things for enough time so that these singular fronts have time to interact in the region that you still control. And remarkably, what you prove is that they just pass through each other like that. Okay? So this is their theory of interacting impulsive gravitational waves, and this sort of generalizes some special explicit solutions with symmetry that were first found by Kahn and Penrose. So actually, there's also an analog of this for weak null singularities. Of course, weak null singularities are more singular. You can never talk about extensions as solutions of the Einstein equations beyond. Okay, but he showed that, again, you can sort of arrange this data so that you have a weak null singular boundary, which sort of joins up with another one, and this is a bifurcate null boundary. Okay? So you should sort of think that, oh, maybe I have to raise the board. So if you believed in this extrapolation, that's sort of reminiscent of maybe what would happen here. OK. So these are the results of Luke. Of course, these are purely local results. And they don't say anything as to whether you get sort of, they don't say anything per se about what happens inside black hole interiors. They don't say sort of whether the boundary of space-time that arises dynamically from, in the context of solutions which are nearby to the Kerr solution, will have such null boundaries, and whether these null boundaries will be singular in sort of the sense that appears in his theorem, because he puts in this singularity into the initial data, and it's a very specific thing. But secretly, that breakthrough is the most important element in the following theorem, which is joint work of mine with Luke, which says the following. Right. But I can still erase what Jacques did. I don't want anything from Jacques' talk. So the theorem says the following. So if I now pretend I know, pretend I know the stability of Kerr in the exterior. Okay? Let's assume the stability of Kerr in the exterior. So that's to say, suppose that I know that, because presumably if you believe the stability of Kerr in the exterior, then if you have Cauchy data like this, which is sufficiently near Kerr, okay, then the space-time will sort of dynamically approach another version of the Kerr family. So there'll be two event horizons, okay? So let me just have chosen this like that. This is Cauchy stability. That's not so important. So space-time will have two event horizons like this, okay? And moreover, the solution will asymptote to a Kerr metric. Of course, it will be a different Kerr metric in general. So a different one here, and a different one here, and different from the one I started, but nearby, at a sufficiently fast polynomial rate. So let's suppose that I knew that. I had proven that. So let me erase all this and just start the problem on the event horizon. Okay? So, okay, that was sort of motivation. So I'm just going to pose initial data on a bifurcate null hypersurface like this. And the data will be, so these will be affine complete null hypersurfaces, such that the data is chosen in such a way so that I approach Kerr data polynomially exactly at a rate which is sort of within what is expected sort of by the conjecture of the stability of the Kerr exterior. Okay? So I begin with initial data like this on the event horizon. So the theorem is the following, that the evolution of this initial data looks like this. So its boundary is null. Okay. And moreover, the metric, I can continuously extend it beyond. Continuously. Globally. Globally. So a corollary of this theorem is the following. That if you believe the stability of the exterior region of Kerr, which I think everyone believes, all right, then not only is the exterior stable, but the Penrose diagram of the whole spacetime is stable, the whole interior. So in particular, sort of if you believe sort of going from here to here, that's the stability problem. Okay, then small perturbations of Kerr initial data, their Penrose diagram will look like this. And the maximum development will still be extendable continuously. Okay, the metric continuously. Moreover, all finitely living observers will enter into the extension. So in particular, given the stability of the exterior, very strong cosmic censorship, and thus also BKL, as usually understood, is false. Okay? So that's a corollary of this theorem. So let me sort of briefly end with what's left to be done around these problems. So open problem 1 is, of course, to prove the stability of the Kerr exterior, namely that indeed small perturbations of sort of Kerr initial data, all right, will indeed lead to black hole solutions. So you'll have complete future null infinity, such that in the past of future null infinity, you will approach another member of the Kerr family at a sufficiently fast polynomial rate. Okay, so that's if you want to open problem 1. Of course, this has independent interest, but in particular, it sort of given this, then this would be a definitive disproof of very strong cosmic censorship and the usual understanding of this PKL conjecture. So let me just maybe remind you what are the prospects for resolution of this problem. So of course, I mentioned earlier that the Poorman's linearized problem is now completely resolved in the full subextremal range. So by Poorman's linear problem, I just mean the question of the understanding the behavior of linear scalar wave equation, box C equals 0, in the exterior region. So in particular, the solutions are bounded, and by boundedness, I mean this sort of statement that does not lose derivatives. It's actually very important for nonlinear applications, that sort of the boundedness statement does not lose derivatives. Otherwise, you start using Nash-Moser. But also sort of decay. So, of course, there's a long history of this. Many people in this room have worked on this problem, sort of in the Schwarzschild and then in the slowly rotating case. And there are also variants of this which are very interesting in the case of cosmological constant, work of Vasi and Dyatlov in the positive case, and Holzhegel and Smulevisi in the negative case, the case of Kerr anti-de Sitter. In fact, in the negative case, it's quite interesting because the sort of decay rates that one prove are only logarithmic, and this does not necessarily suggest nonlinear stability. So that's a whole interesting story. So also very recently, the true linearized problem has been resolved. This is a theorem which will appear shortly, but only in the Schwarzschild case. Okay. So what we prove is that Schwarzschild is indeed linearly stable as, that's to say, solutions of the linearized Einstein equations, not this Poorman's scalar wave equation. The linearized Einstein equations, they remain bounded in the exterior. And again, it's extremely important that this boundedness statement does not lose derivatives. And decay, of course, now the best you can hope for is that they decay to a linearized Kerr solution, because, of course, sort of the linearized Einstein equations around Schwarzschild certainly see the linearization of the Kerr metrics. So those are special solutions of that system, and this is the type of state that. In view of these results and many others that have been proven by various people here, that suggests that one should soon be able to indeed understand the nonlinear dynamics of the Einstein equations in the neighborhood of Kerr initial data in the exterior. Okay? So that's open problem 1, which good for people here to keep in mind. So what is open problem 2? So I said that this theorem completely resolves the understanding of the black hole interior, but actually, of course, we have only in some sense resolved half of the problem. And I don't mean sort of, I mean assuming the exterior, we still have only resolved half of the problem. And the reason is that I've only told you in what sense this boundary is regular. I have not told you anything about this boundary being singular. And again, if we go back to our good old extrapolating linear theory, which now it seems was not such a stupid thing to do after all, then in linear theory suggests that even though C remains bounded, derivatives of C should not be square integral locally. Okay? Even in the context of linear theory, again, this is not a theorem, it is a sort of conditional theorem. It can be proven under some extra assumptions. Okay. So a natural conjecture is that this is exactly the case here. That's to say, for generic initial data, okay? Obviously, this statement cannot be true for all initial data. That's the Kerr solution, for instance. All right? But for generic initial data, this hypersurface should be singular in the way that you see by extrapolating linear theory. Namely that the Christoffel symbols of any continuous extension should fail to be square integral. So if this were true, then some version of strong cosmic censorship is still saved, namely the version of strong cosmic censorship. So let's go back all the way to the beginning. The version of strong cosmic censorship whereby suitably regular, you mean as a manifold with locally square integrable Christoffel symbols. So this notion of inextendability was formulated by Christodoulou, actually sort of motivated by this spherically symmetric toy model and the fact that this is exactly what appeared there for the first time. And its sort of motivation is that, well, this is not the strongest type of inextendability that one can hope for, but at least it tells you that you cannot continue as a weak solution of the Einstein equations. Okay, so this is exactly what already I noted in discussing Luke's theorem, okay? That if you put in this type of singular behavior, then it does not make sense to talk about the solution beyond this boundary as a weak, even a weak solution of the Einstein equation. Okay, so that is open problem 2, and maybe I should say that actually the spherically symmetric version, toy model version of open problem 2 is actually an old result of mine that dates back to my PhD thesis. Again, it's not completely satisfactory in that the result that I could say says the following, that if you give me a lower bound, polynomial lower bound on the decay rate of a scalar field, so this toy model is sort of Einstein gravity coupled to a scalar field. If you give me that lower bound, then I can prove exactly this inextendability statement. Okay. And one good thing about preparing your talk the night before is that you can also refer to things that just appeared on the archive today. So in particular, there's some recent work by Costa and collaborators, which is a version of these results in the spherically symmetric toy model in the case of cosmological constant. And the one thing I want to emphasize is the following, that in the case of positive cosmological constant, you again have analogs of this because you have Schwarzschild de Sitter and Kerr de Sitter. And actually, in some sense, the singularities, they only get weaker. And how weak they are depend on the distance to extremality of the parameters. And there is some regime where actually sort of this Christodoulou formulation will not hold in the toy model. And that's actually very, very scary for the sort of physical interpretation of the theory. So this is something to keep in mind. It's actually very interesting to look at this case. So finally, I'll offer you an open problem 3 in view of this connection of the Blueshift instability with scattering theory. So the open problem 3 is the following. So suppose I don't solve the sort of forward stability problem, okay? But I try to construct black hole exteriors, okay, by imposing initial data on H plus and I plus, just like in the scattering theory for the linear wave equation, but now for the nonlinear Einstein equations. And I solve the Einstein vacuum equations backwards, okay? So actually, there's a recent theorem of mine with Gustav Holzhegel and Rodniansky, where we showed that if you impose exponentially decaying at a suitable rate free data here and here, okay, then you can indeed solve backwards. So you create a space-time in this region here, which dynamically approaches Kerr. So this is a way to, if you want, give you first examples of dynamic spacetimes that dynamically approach Kerr. Okay? And of course, the reason that you need to impose exponential decay here and here is the Blueshift when you solve backwards. Because this theory is taking place in, if you want, in the sort of non-degenerate energy space. And I just told you that in the case of the linear wave equation, the non-degenerate energy space is Blueshift. So now we all believe that generic solutions of the forward equation, you'll have polynomial decaying sort of free data here and here. So what happens if I impose polynomial decaying free data here and try to solve backwards? So sort of the worst case scenario is you just can't solve. You can't do anything. In fact, that's what's analogous to the initial expectation of a space-like singularity in some sense. Okay? But now we know better. So the conjecture I offer is that what you can still solve backwards, but what you'll get generically is the event horizon itself will be a weak null singularity. Okay, just like here. So so that's a nice open problem. So let me just give. You might worry about this problem because at least in the Kerr case, even if I look at the scalar wave equation, it's not clear that there's any analog of a scattering theory in the sense that there was for Schwarzschild. Because in the Schwarzschild case, the scattering theory that was not Blueshifted is based on d by dt vector field, which is time-like in the exterior. Okay? Whereas in the Kerr case, sort of all the theory, everything that we know, is based only on sort of energy currents that correspond to vector fields, which I'll call capital N, which are time-like at the horizon. But it turns out that actually sort of a not so difficult variant of our recent work on the forward problem for the sort of scalar wave equation on Kerr allows you to sort of also do the theory with respect to a vector field which is not time-like, but which is sort of exactly analogous to this d by dt in Schwarzschild. That's to say, a vector field which is killing in the neighborhood of the horizon and killing in the neighborhood of null infinity. So in particular, you can show, so I'll call this vector field V. So in particular, you can show that, first of all, that the forward map is well defined in the energy spaces corresponding to this vector field, and moreover, that it is invertible. Okay, so it's no longer an isometry. This vector field is not killing everywhere. It's only killing in the neighborhood of H plus and plus, but it's invertible. So a corollary is you can define the usual sort of scattering maps, sort of either from initial data to horizon plus infinity, or from past horizon, past infinity, to future horizon, future infinity. So there's also some sort of related work in the cosmological constant case by Georgescu, Gerard, and Hefner in this direction. All right, so let me end with some final remarks. So what we see in particular is that if you look at small perturbations of two-ended Kerr, at least if you believe that open problem 1 will be resolved soon, then this tells you that there is no space-like singularity in spacetime, period. There's no space-like singularity for small perturbations of two-ended Kerr data. So in the moduli space of solutions of the Einstein vacuum equation in the neighborhood of Kerr, no space-like singularity. Okay, for no open family in the moduli space will contain. Okay. But you might wonder what happens in the case where you have, let's say, black holes that come from gravitational collapse. So I'll make a schematic space-time diagram like this. So black holes that only have one end. Okay, because you might think that this situation, the fact that the whole boundary is null, is related to the fact that you had these two ends and they came together. So, of course, if you know that this black hole asymptotes sufficiently fast to Kerr, then just by causality arguments, these results still apply to tell you that part of the boundary is null. Okay, so if you sort of want the whole boundary to be space-like, that's also disproved in this case. Okay, the part of the boundary is always null, and that's just a fact of life. But you might wonder, is the whole boundary null here? Is there maybe still a space-like part, or does this somehow close up the space-time? And that's, I think, sort of the next thing to probe as far as sort of the question of what do generic sort of space-time boundaries look like. So I'll leave you with the following thought, that it really used to be the case that any time anyone would talk about null singularities, it's sort of like something, you're talking about something crazy. And there really was a question, do these exist anywhere in the moduli space? Not if they're stable, even if they're explicit examples. And now I think the real question is, are there anywhere in the moduli space regions where you have space-like singularities for an open set? Anywhere in the moduli space. That's now completely unknown. And I think, in some sense, the whole way the discussion was formulated because of BKL was disorienting. And I think this is really what one should probe in order to make further progress on this issue. Yeah, so let me end there. Thanks.